Hi, in this video I'm gonna go through the basics of waves. So what do we mean by a wave? Essentially we mean what you think we mean by a wave, but let's try to make that precise. So one way to say it succinctly is this. We've got some kind of displacement in a so-called medium, we'll talk about that more as well, and that displacement is traveling through that medium from one point to another. So let me give you some examples. It's best illustrated by example, so we see what that means. So here are some examples. Ocean waves, right? Or any type of water waves. What's this displacement in that case? Well, a wave, the thing that's getting displaced is the surface of the water. It's going up, down, right? So it's vertically displaced, but this vertical displacement is moving sideways across the ocean. You take a wave on a string. So imagine you take a long piece of string and you tie it on one end to a chair, you hold on the other end, you pull it tight, and then you flip your hand up and down, and you're going to see this little pulls traveling along the way, along the string. Right, so what do you have there? You move the string a little bit, that creates a small displacement in the string, up, down, or left, right, and then that is traveling down the string. Sound waves. Sound waves, that's why you can hear me right now. What are those? Well, if you could zoom in essentially at the air molecules and look at them more closely, you'd see that these air molecules would be closer together, higher density in some places, and that sort of patch where the air molecules are denser keeps moving along. And patterns in denser and less dense air. You also think of it in terms of air pressure being higher and lower, higher, lower at certain intervals. No single air molecule goes from, say, your vocal cords to somebody else's ear when you talk to them. But it's this sort of displacement of one of them that gets past the next one, to the next one, to the next one. Electromagnetic waves, right? Very important example, such as light, or radio waves, gamma rays, X-rays, microwaves, ultraviolet, infrared, right? The whole electromagnetic spectrum, as it's called. What's that? Well, in this case, it's a little bit harder. It's not some physical thing that's moving, but it's electric and magnetic fields that are flipping up, down, up, down, up, down. And this up-pointing electric field is moving along, and then there's a downward-pointing field coming right after it. Similarly, with the magnetic field, I'll show a picture of that to you later. Some more examples. Seismic wave, right? Like earthquakes. They are waves traveling through the Earth's crust, or to some extent the mantle as well, depending on the type of wave. So there, literally, it's a chunk of ground, essentially rock, that's moving sideways, briefly, or shaking back and forth, and that shake is traveling along. It's not like a piece of ground moves from one part of the Earth to another. Yes, there might be, changes, permanent changes, but no piece of rock is moving from the epicenter of the earthquake to where you are 300 miles away. But what is moving is this brief pattern of displacement. Gravitational waves, it's been in the news over the last couple of years, because they were discovered. They'd long just been a prediction of general relativity. What's that? Again, it's kind of hard to explain, because to do it in full, we'd need to understand general relativity, but essentially it's a small disturbance in the gravitational field. In the same way, electromagnetic waves are disturbances in the electric and magnetic field, while this is a disturbance in the gravitational field, which, if you go deeper, is small disturbances in the geometry of space and time. What does that mean? Different story, not part of this course. So let me then make a few general points about waves, so we understand a little bit more about what they are and what they do. So as I indicated already, there's nothing physical. It's moving from one place to another, right? If a wave travels from, say, a boat out in the ocean, produces a wave that travels to the shore. It's not that the water in front of the boat moves to the shore, right? If you take a patch of water, like a blob of water in front of the boat, you dye it red, that red blob is not going to move to the shore. It's the pattern of displacement that's moving, right? So waves are moving patterns, not moving physical object or physical substance. Another thing to note is that waves can move in one dimension or more dimensions. So one dimension example would be a wave on a string. Like again, the example I mentioned earlier, imagine you have a string and you tie one end, to a chair, a table, or to something. You pull it tight and you can flip your hand up and down, holding onto the other end, and that'll make a little sort of pulse travel along it. Right? It's only going along a straight line along the string. Motion in one dimension along a line. If you've got water waves, right, if you imagine you drop a pebble into a lake, it creates waves. They move along the surface. So the surface is a surface, it is two-dimensional, right? It can go forward, backwards, left, right. So that's how the wave spreads out in essentially rings. Right? A ring, a circle, a growing circle, that's a two-dimensional shape. Also can have three dimensions. For example, if you turn on your speakers, they produce sound. Well, the sound is going in all directions in the room. Turn on a light bulb, the light's spreading out in all directions in the room, right, in three dimensions. So it depends very much on the type of wave, the medium, and so on. So another point about waves that is just terminology we need to understand is that waves can be longitudinal or transverse. Now what does that mean? Essentially it relates to the direction of the displacement in relation to the direction in which the wave is moving. And I'll show you some examples later, in just a minute. Right. The definition is that a wave is longitudinal if the displacement is in the same line as the motion of the wave. It's transverse if the displacement, the pattern that's moving along, the displacement is perpendicular to the direction of motion of that pattern, right, of the wave. This sounds a bit abstract. We'll look at some examples in just a second. Now notice that some types of waves, they can be both transverse and longitudinal. And again, I'll show you some examples of that as well. Now, the waves will travel with a certain speed, and in most cases, the speed is fixed by the properties of the medium. Right? So waves, the speed with which, say, ocean waves travel, depends on the nature of water, and to some extent also the depth of the seafloor. Which is why waves break. When they reach the shore, it becomes more shallow, the wave slows down, so the top part of the wave has too much momentum, it sort of falls over the bottom part. The case of a string, if you got a string and you pull it tight, well, the higher the tension in the string, the faster the waves will travel. With something like light, light in vacuum has a certain fixed speed, right? It's a famous fact, I suppose. But if light travels in a medium, such as that's not just vacuum, say through glass or through water, that'll actually change the speed. We can talk a little bit more about why that is, although ultimately the explanation involves some fairly advanced electromagnetism. Okay, so just some general points. There's some more things to talk about. So here there's two sort of different wave patterns that you might think of, two types of patterns. One is one that is sort of a finite extent. Like again, think of the string, right? I have a string and I wiggle it up and down once, and you can see this sort of pulse going along it, and in front of it it's flat, behind it it's flat, and eventually it will hit the chair, or whatever happens, it will fizzle out, and we're back to a straight string. If you look at something like the ocean, it's more like it's a continuously new waves are arriving, right? It's a continuous pattern, it keeps moving, it doesn't really ever stop. Maybe if you wait a few hours or days until the sea is calm, right? But within this sort of time frame of waves moving towards the shore, this pattern doesn't really change. Now, for most of the part of this course, we're going to look at at continuous waves, specifically waves that are sinusoidal, so have a sort of sine or cosine shape. And there are reasons for that. One reason is that they exist in nature. We'll figure out why. The second reason is that if it's some other shape, we can still mathematically represent it as a sum of different sine functions. And this is a very sort of fundamental, useful fact in a lot of areas of physics. The fact that any sort of shape you might think of, pretty much, can be represented by a sum of sine or cosine functions. And we'll talk about that a little bit more too, although the full understanding in terms of mathematics will have to wait until you've covered some more aspects of advanced mathematics. But we'll cover the basics of it. Okay, almost there. Waves carry energy, right? So nothing is physically moving, but they can still carry energy. Right? That is why there's life on Earth, because there's electromagnetic radiation from the sun, little up and down flipping electric and magnetic fields. This disturbance in the electric and magnetic field reaches the Earth, and it gets picked up through various physical processes, warms up the Earth, makes life on Earth possible. Right? So energy is transferred via waves. How much depends on the type of wave, depends on the particular properties of the wave, the size of the wave. We're not going to talk about it that much, but we'll investigate this a little bit too. Now, how do I picture particular waves? So what I've done so far is I've drawn what you call a snapshot graph. Right? A snapshot graph, and it's literally what you think it means. But imagine you take a camera and you take a picture of the wave. It'll show you what the wave looks like. Now, it'll show you the wave at one particular instant, right? If I waited a tiny bit, a fraction of a second later, this sort of peaks would have moved sort of over here, and the wave might look like this. If I waited a little bit here, then the wave might have looked sort of more like this, right? The whole thing would have moved over a little bit. So a snapshot graph shows you the displacement, say, of the surface of the water, of the position of the string, the value of the electric field, whatever it is, it shows you the displacement against position, but only at one given time, like an instant at which you took that picture with your imagined camera. If you want to have more of an idea of what happens as time goes by, you can look at what's called a history graph. And when they ask you that, you might just check a textbook for some examples of what those look like. They should look fairly similar on paper at a first glance. But the history graph is a displacement versus time graph. So imagine you pick this point here and you put a rubber duck here, right, on the ocean water. And the rubber duck is going to go up and down, maybe also left and right a little bit. That motion of the rubber duck you could represent, right, as a function of time. What's the vertical displacement of the rubber duck as a function of time? What will that give you is what's called a history graph, right, as I said. It's the history of the displacement at that point, right? The history graph does not tell you what happened over here at any time. Maybe you'll be able to infer it, but it literally only talks about this point, but for all times. Unlike the snapshot graph, which looks at all of space, but only at one particular point in time. Right? Because the displacement, say, here depends on both where is it here, or here, or here, or here, which point do I pick, but also on time, right? It changes with time. So the displacement is a function of position and time, which is hard to draw on a single graph, which is why you often see choices made to pick either one of those two. In practice, more often than not, the snapshot graphs tend to be more useful because they give a very direct visualization. Okay, so let's just, to finish off this introduction, let's talk about some examples, just to make this more concrete. So the first example is very artistically drawn here by myself. The example I've been mentioning, you put a string and maybe the other end is tied to something, so it's a taut string. You move this up and down and you get this sort of pulse traveling along it. So what's moving along is no piece of string is moving from here to here, but it's this pattern of displacement, here represented maybe by those blue arrows, that's traveling to the right. So, because the displacement is up and down, but the pattern is traveling to the right, this wave is a transverse wave, right? Let's look at the definition again. The definition of transverse was that the displacement is perpendicular to the motion of the wave. Well, that's exactly what's happening here. The wave moves right, but the displacement is up and down. So this is a transverse wave. And the wave speed depends on what type of string you have, what's the tension in the string. We'll actually prove that in detail later, this example. Another type of wave might imagine you have a slinky, right? It might be this. So you have a slinky, and maybe the other end again is tied on somewhere. Now, of course, you could do the same thing you did with the string and move it up and down. But the other thing you could do is you could move your hand forwards and backwards. If you have a slinky, go and do that. And then what happens is that these sort of areas where the windings are denser, they move along, and the areas where the windings are more open, they move along, right? So you can sort of send little pulses down. So in this case, if I look at like a single piece, say here, right, it's going to move to the right, to the left. In the end, it's going to end up where it started. But this displacement left or right, that's what gets passed on to the next winding, the next little chunk of metal that's part of the slinky. So because the displacement is left-right, and the pattern still moves right, I have it down here, right, moves to right, they're in the same direction along the same line. So this is a longitudinal wave. Another type of ocean waves, we already talked about those. Two, again, they're very easy to visualize. Now, if you look very closely, you would actually notice that if I put a rubber duck here and I watch its motion carefully, it would not just be going up and down, but also left and right a little bit. It's harder to see when you just look at the surface of the water because you can't identify a single patch of water and see what it does. So we see the up-down motion is also a bit of a left-right motion. What does that mean? It means it's both longitudinal, it's the left-right motion, the same direction as the wave as a whole, but also transverse, right? It's going up and down, perpendicular to the direction of the motion of the wave. So this is both longitudinal and transverse. And final example, electromagnetic waves. So here's what they look like, right? And how do they exist? Well, they're essentially take Maxwell's equations, right? The equations that describe all of electromagnetism for practical purposes. You take those equations and you can show that one solution that they allow is this sort of oscillating electric and magnetic field. And they oscillate together, and they oscillate at 90 degrees to each other. So here the blue arrows are meant to be the electric field. They go up, down along the vertical axis. And the magnetic field then would go along the sort of sideways axis. And this whole thing travels down in the third direction. So then they require 3 dimensions. But because the displacement either up, down, or along this axis, it is a transverse wave because there's no electric field or magnetic field vector in the direction of motion, which is in this direction the way I've drawn it. Right? So this is a transverse wave. Like it's 2 waves traveling together, electric and magnetic field, but the laws of physics demand that they travel together. You can't have one without the other. So it's really, you think of it as one wave, an electromagnetic wave, which is a disturbance in the electric and the magnetic field. So that's the basics of waves, understanding what they are, what they do. In the next video, we're going to analyze them a bit more quantitatively. Thanks for watching.